All right, so let's talk about this Data Encryption Standard. So actually, it is no longer used, but we have to talk about it. This is why we are talking about it. So let's look at the history first, then we will see the design criteria, arguments, and then we will talk about the security of it, and then the modifications like triple this and so on. So let's start with the history. NIST initially had a different name. They were called U.S. National Bureau of Standards, NBS. So in 1973, they called for a proposal for a block cipher suitable for federal use. Okay. So initially, I think people submitted some, but NIST didn't like them. So they asked again, and in the second call, IBM said that since we have already have a good block cipher called Lucifer, we can modify it and then submit to this call for proposals. So NBS liked this, but NSA made a few tweaks to this cipher. So they shortened the key. For instance, Lucifer had 128-bit key, but now DES has 56 bits. So they said that this is enough, but actually it is not. So this modification weakened the cipher, but NSA also tweaked the S boxes, but this strengthened the cipher because they knew the differential cryptanalysis, and they also knew that other countries also knew differential cryptanalysis. So they wanted to have a cipher that is resistant to differential cryptanalysis. So you can see that these days from 1970s. And Biham and Shamir discovered differential cryptanalysis in the 1990s. So secrecy agencies knew this technique in early days, and some Japanese documents kind of show that Japanese knew this cryptanalysis techniques as early as the Second World War. Okay, but we will come to differential cryptanalysis in a minute and see what we mean. Okay, so this algorithm, this currently known as Data Encryption Algorithm, DEA, since it is no longer a standard. This is really very, very important. Since it's a standard, people still think that this is a standard, and people are still using this. They should stop using it in 1990s, but it is 2022 now, and people are still using this. Okay, so this is a huge problem. Again, a few years ago, when you Googled Microsoft and encryption, you will find a blog in the Microsoft.com explaining how the encryption works, and they were showing you how you can do it using this, even showing some pseudocodes where you can use in this in Windows. Okay, so it became useless after 1990 since its short key is susceptible to brute force attacks. Okay, performing 56-bit key exhaustive search attack, I think you can do it in a few hours. If you are a secrecy agency, if you have a lot of GPUs, you can do it in a few hours and so on. With a single GPU, it takes a few months. Okay. Again, still, it is one of the most widely implemented cipher in the world. So early reactions, MBS organized 2 public workshops. Diffie and Hellman claimed that a machine can be built for $20 million to perform exhaustive search on 56-bit key. So people were, at the early dates, clever enough to say that this key is short. But MBS responded that such a machine would cost over $70 million to build between 1977 and 1990s, be 256 feet long, so they are claiming that it will be a very huge computer, and draw millions of watts of power. So they thought that nobody can do it at the time, but of course, NSA had the supercomputers, and they could break this key length in 1980s and around that time. But in the early reactions, analysis of S boxes showed that they are carefully chosen. But they didn't know that IBM's S boxes weren't as strong. So these S boxes belong to NSA. Some speculated that there might be a trapdoor in the algorithm so that an additional piece of information may allow unauthorized decryption. So this conspiracy theories always exist, People think that maybe there's a secret password where you use it and, get access to everything. So this is what they're trying to say. So they think that maybe with a little bit of information, you can decrypt everything. But to the best of our knowledge, after these 50 years, we haven't observed such a trapdoor. So we don't think that there's such a trapdoor. Here, the trapdoor is the short key. You know, in the 1990s, in the 1980s, you don't have that much amount of computational power, but the secret agencies does. Okay. So academics failed to provide successful attacks until 1990. In 1992, Biham and Shamir provided the first theoretical attack, differential cryptanalysis, on this, which requires less time than exhaustive search. However, However, the attack requires 2 to the 47 chosen plaintext to be captured, which is unrealistic. So they provided an attack which is faster than exhaustive search. Recall that the exhaustive search requires 2 to the 56 encryptions or decryptions. Here, they can break the cipher less than 2 to the 56 encryptions, but the problem is that they have to listen to the communication, capture ciphertext, but those ciphertexts should belong to some specially chosen plaintext, and the attacker should also know those plaintexts. Only then the attack works. So this was a little bit surprising, because when Biham and Shamir discovered differential cryptanalysis, they practically broke some of the ciphers. So they were expecting to break this in practice, but they realized that these S boxes are stronger than the S boxes of the block ciphers that they broke. But 1 year later, Matsui provided the first experimental cryptanalysis of this by introducing linear cryptanalysis. It also required too much plaintext ciphertext pairs to be captured to perform the attack. For his experiment, Matsui generated the pairs with 40 days of continuous encryption using all of the PCs available to him where he worked in, which was Mitsubishi. I think he still works there. So in 1994, Coppersmith, one of the designers, confirmed that NSA tweaked DES to resist differential cryptanalysis. So I think in the following slides I will explain it, but if I don't, in case, let me explain it here. So Coppersmith and other people, once NSA changed their S boxes in 1976, they looked at their original design and the NSA's tweak to understand why they changed the S boxes. And then by working on this, they realized that they can break their cipher in a very easy way, and they cannot break NSAs. So they realized that if you make small changes in the plaintext in their original design, it makes some anticipated changes in the ciphertext. So with some probability, they can anticipate what kind of changes that are going to happen in the ciphertext. So they call this attack T attack, from tickle attack, from the word tickle. And they went to NSA saying that we understood why you change our S boxes, because this way now it is secure, but in the original version we can break it like this. So NSA told them, yes, we knew this technique too. This is why we changed the S boxes, but keep it secret because we are using it to listen to other countries. Okay, so almost every secrecy agency knew this technique, but academics only discovered it in the 1990s. So Biham, I think 5 or 6 years ago, became IACR fellow and gave a talk. And the talk title was "How to Make a Difference," since in the differential cryptanalysis you introduce differences. So this was his title. So at the end of his talk, he thanked every secrecy agency who knew this technique and didn't publicly announce it, so that he took all the credit. Okay. So after these theoretical attacks, now we have practical results. There was a Deschalt project. So since we had the internet at that time, some volunteers connected to a server, and there were around 80,000 PCs, and they tried to perform a brute force attack on an encrypted message. So this way they actually found the secret key and obtained the plaintext. So in 1998, now we have a hardware. EFFs designed a special machine containing around 2,000 custom chips, which they call DES cracker. And this device breaks this key in 56 hours. As you can see, the year is 1998. but I still talk to some engineers saying that this is still secure. Okay. This is only allowed in legacy systems. Triple DES will remain as a standard at least until 2024. So I modified this sentence because in the earlier versions, I wrote it here 2030, thinking about NIST's claim that they will allow 112-bit security until 2030. So NIST still says this, but in a different document, they say that they will not allow the use of triple DES after 2024. So most probably in the IOC standard, it will stay as a standard after 2024, but it will not be a NIST standard. So you will not be able to use triple DES in United States, and we will see what happens. But most important thing here is that this trained a generation of cryptographers. We learned a lot in terms of designing a cipher, in terms of cryptanalysis, finding new techniques, and so on and so forth. This is why actually today I'm still talking about this. Okay, so again, I'm also trying to explain why you shouldn't use it. Okay. All right, let's now look at the definition. DES has a block size of 64 bits, like in the case of present, but the key length is short, 56 bits. Something that the key length is 64 bits. This is a mistake because you really chose 64 bits, but you have 8 bytes, and most significant bits of these bytes are parity bits, so you don't have any control over them. So in practice, you have only 56-bit secret key. The round number is 16. So in the present, we had the SPN cipher. Now we have a face-tell cipher. So for the following slides, we enumerate the bit positions from left to right. The leftmost bit position of the 64-bit block is denoted as 1, contrary to the present. So recall that in the present, I started from 63 to zeros. Now I'm starting from 1 to 64. So this is old way of actually enumeration. Modern ciphers generally use the rightmost bit as the 0th bits. But just so it is really confusing, and it is really hard to read the old NIST document about this. But this is how it works. Okay, so let's recall how the face-tell ciphers worked. So recall that we had a key, and from the key schedule we have the round keys. But in a single round, what we do is as follows. We divide the plain text into two parts, right and left. So right part actually is not modified and becomes the left part in the next round. But right part also is fed to the round function, where you apply, confusion and diffusion layers. And the result is XORed with the left part. So left part is modified here, but the right part is not. So you swap them. Now the left part is becomes the right part here, and goes here unmodified, and so on and so forth. Generally, in the last round, we don't perform the swap operation because for the case of security, it doesn't provide you any security. So you save the time here. But of course, for hardware, sometimes this is problem because here you are breaking the symmetry. Because if you implement it as this, the round function and the swap operation, you can perform the remaining parts in a for loop, but here you have to change it. So this is actually what happens in AES also. I will explain it when I talk about AES. This is why in the Intel CPU instructions, you have a different instruction for the last round, because in AES, we will not have the matrix multiplication in the last round. Okay. So let's look at the picture of this. As you can see, this is the face-tell part. You have the plain text. You perform initial permutation and at the end final permutation. I will show you the details. The right part becomes left part here, but right part is first expanded. There is an expansion function, XORed with the 48-bit round key. Then we have the function here which performs S boxes and permutation. Okay, and as you can see, from the master key, it is also divided as the right and left, but first you perform a permutation. You perform some rotation, sometimes 1 bit, sometimes 2 bits, depending on the current round. And then you also perform a permutation. So from the 64-bit, you actually provide 48-bit round keys. Okay. So now we will look at all of these details. So I think probably we will start with IP initial permutation. Okay, so this part also has a picture. I told you that first you have an expansion function. So as you can see, the right and left part has to be 64 bits. But this expansion extends this 32 bits to 48 bits. Then you perform the key XOR. Then you reduce it from 48 to 32 again at here. So in more detail, your 32 bits. Some of the bits are repeated here, as you can see. This is why you expand 32 bits to 48 bits. You XOR it with the round key. Then 8 S boxes are applied, but these S boxes have 6-bit inputs, but provide 4-bit output. This is how you reduce 48 bits to 32 bits, and then you perform a permutation. Okay, so we will see details of all of these steps in the following graph. So let's start with the initial permutation. So you have the block, which is 64 bits, and the following permutation is applied. So this means that 58 bits of the input is put here. It becomes the first bit of the, after this permutation. So 58 bits comes here, 42 bit comes here, and so on. So here you are actually modifying the bits of the input. So cryptographically, this doesn't provide you any security or anything. But this permutation, as you can see, it is you can see that differences are 8. So we are actually talking about bytes here. So in hardware, this actually allows the desk chip to read the input in a fast way. This is why you have this initial permutation. And the final permutation is just the inverse of this initial permutation. So in terms of security, this doesn't affect anything. So in cryptanalysis, actually, we act like as if there isn't, we don't have these permutations. It doesn't affect the attacks. Okay. So again, initial and final permutation, just the inverse of the initial permutation. After round 16, a final permutation, which is the inverse of initial permutation, is applied to the output to provide the cipher text. When the attacker has a cipher text, they can undo the final permutation. When the attacker has a plain text, they can undo the initial permutation. So in a chosen text attack, IP or the final permutation have no cryptographic value. Okay. However, this is designed for hardware, and IP is designed so that it provides a suitable ordering of bits when loaded from input device to the desk chip. That is the whole idea. So this is why in the modern ciphers you don't see this kind of stuff. Okay, this is what I'm trying to explain. All right, let's look at the key schedule first. 64-bit user key is taken, but the most significant bits of the bytes are used for parity. So the effective key is 56 bits. First permutation, PC1, is applied to remove the most significant bits and permute the 56 bits. So this is why your effective secret key is 56 bits. Then 56-bit key is divided into two 28-bit parts, and they are rotated by Ri after round I. So Ri is maybe 1, sometimes 2. Here you can see when it is 1 and when it is 2. So in the first round it is 1, but first in the 7th round it is 2. Okay. A permutation PC2 is applied to obtain 48-bit round key. So let's look at them in detail. This is your permutation 1. This is your permutation 2. So as your input, you have the 64 bits, but here you reduce it to 56 by removing the parity bits. Then from this, you obtain you perform this. So you perform some rotation to these bits. Then you perform permutation 2, which is actually 48 bits, as you can see. Okay. So since the master key is larger, 56 bits, you reduce it to 48 bits. So some of the bits is not used in the round key. But after the key schedule, so since you perform rotation and so on, those unused bits maybe will be used in the following round. So the question is, how many times of a bit of this master secret key is used in the rounds? So this is what they analyzed in the earlier analysis. So they check the frequency of key bits. Every key bit should have almost equal effect on round keys. This is what we hope. But in this, as you can see, the parity bits are not used from the 64-bit supplied key, so the frequency is 0 since they are removed in the permutation one, PC1. But as you can see, these bits of the master key only appear in 12 of the round keys. So attackers generally try to focus on this, so since they have less effect and so on. But almost every bit appears more than 12 times. So it looks like the frequency is good. So this looks like they didn't put any, backdoor or anything to some of the bits. So we covered the key schedule. We talk about initial and final permutation. Now let's look at the inside of the cipher, which is the round function of this. So round function of this contains the following operations: expansion, key addition, substitution, permutation. Expansion, as I told you, takes the 32-bit input and expands this to the 48-bit. So 32-bit input, which is the right half of the intermediate block value, is expanded to 48-bit intermediate value by duplicating its 16 particular bits. Design rationale here is that any two neighboring S boxes share two input bits. So this is why they are actually cloning some of the bits. So expansion is as follows. So your input is 32 bits. So 32nd bit appears as your first bit. But as you can see, 32 appears again here in this picture. So it is duplicated. 1 also appears here and here. But most probably 2 only appears once because you are only cloning 16 bits. So 16 bits appears twice, but 16 bits appears only once. So this is how you perform the expansion. But again, the design rationale is that any two neighboring S boxes share two input bits. Okay, this is the idea. Key addition is simple XOR operation. 48-bit round key is XOR to the 48-bit intermediate value. Round keys are generated by the key schedule algorithm, which we have already discussed. In the third step, you perform substitution. So the 48 bits are split into 8 groups of 6 bits and used as the inputs of 8 different S boxes. So here is the difference. In the present, we had 16 S boxes, but all of them were identical. Now here we have 8 S boxes and all of them are different. And these are the S boxes that are modified by NSA. So S boxes have dimensions 6 times 4. So they take 6-bit input and 4-bit output. So as you can see here, you also have an information loss. You cannot, this is a one-way operation. You cannot go from 4-bit to 6-bit. Okay, this is against information theory, But we don't need the inverse operation because this is a phase-test cipher. So if it were SPN, you would lose information, so you wouldn't be able to decrypt the ciphertext. Thus, the concatenated outputs provide 32 bits of intermediate value. Security depends on the S boxes since they are the only nonlinear part of the cipher. A 6 by 4 S box can be seen as 4 by 4 S boxes. So we will see how it works. The outer 2 bits of every 6 bits represent the S box to be used, and the inner 4 bits are taken as the input. So let's look at an example. So assume that your 6-bit input is this, okay? So we look at the outer part, which is 1, 0. So this means that use the 1, 0 S box, which is, 2 in the integer notation. So you go to P2. And as the input of this S box, you use the middle part, 1, 1, 1, 0. So let me show you how this works. For instance, as an example, let's look at S1. This is a 6 by 4 S box, but we can divide it into 4 by 4 S box. Again, if your input is this, you take the outer part, it is 2, you choose P2. So if your input is 1, 1, 1, 0, this means E, so it is E, so your output should be E. This is how it works, okay? And finally, we perform a permutation to the outputs of the S boxes because that was the confusion layer. Now we have the diffusion layer as a permutation. A bit level permutation is applied to the 32-bit intermediate value according to the following table. It provides diffusion, and the table is as follows. Again, the 16 bits of your 32-bit value, the 16-bit becomes the first bit, your 7th bit becomes the second bit, and so on and so forth. So as you can see, since we are swapping the positions of the bits, this is actually designed for hardware. Okay. So if you go back the whole picture, now you can now you know every inner workings of it. So this is how it works. So it looks like simple, but if you haven't implemented a block cipher before, it is very, very hard to implement it in your first trial and have a correctly working implementation. Okay. Again, this is the inner part. So recall that this is the expansion, key XOR, S boxes, and then the permutation. Then the output of this. So this is your right 32 bits. The output is XOR to the left 32 bits from here to here. That is the whole idea. And we repeat this 16 times. Right? So after this, since people argued about security, some design rationale are revealed, trying to show that they made a good design. So some revealed design criteria as follows. No S-box is a linear or affine function of the input. Changing one bit in the input to an S-box changes at least 2 output bits. So as you can see, they know the differential cryptanalysis, but they're trying to show that they don't know it. So they are giving arguments like this. The S-boxes were chosen to minimize the difference between the number of ones and zeros when any single bit is held constant. Again, this is related to differential cryptanalysis. For any S-box S, SX and SX XOR this differ in at least 2 bits. This is important because if it affects only 1 bit, then you know you can find a good differential path. For any S-box, again, SX is never equal to SX XOR this, where RS can be zeros and ones. So they are actually saying this, but they're actually trying to tell you that it is secure against differential cryptanalysis. So this is the whole idea. And some revealed criteria about permutation as follows. 4-bit, I will explain why we're actually talking about it. So 4-bit output of an S-box affects 6 different S-boxes in the following round. So 4 boxes directly to via the expansion function. So they're trying to show that they chose a good diffusion. If an output bit from S-box I affects one of the 2 middle input bits to S-box J in the next round, then an output bit from S-box I cannot affect a middle bit of S-box I. Again, this is trying to show you the permutation is good. The middle 6 inputs to 2 neighboring S-boxes, those not shared by any other S-boxes, are constructed from the outputs from 6 different S-boxes in the previous round. The middle 10 input bits to 3 neighboring S-boxes, 4 bits from the 2 outer S-boxes and 6 from the middle S-box. In other words, those not shared by any other S-boxes are constructed from the outputs from all S-boxes in the previous round. So as you can see, these are some theoretical arguments, and because actually we cannot prove security by the design. So here actually the symmetric key encryption works like a magic. Because we design something and it works, but we cannot prove why it works. So our only argument is that we try to cryptanalyze it with every cryptanalysis technique we know, and we cannot do it. So this is why we feel it is secure. So here there isn't much. Compared to the public key cryptography, here we are not relying on a mathematically hard problem. Here we are focusing on confusion and diffusion, but since we cannot measure it, we are trying to prove that we chose good confusion and diffusion layers. So this is why we are trying to explain why our permutation is good and why our S-boxes are good. Okay, and so this actually shows you that we chose the best from the possible cases and so on. So this is our arguments. Okay, but now let's talk about some of the properties. This has a complementation property. So we call it a property, but actually it is a weakness. Okay, so it works like this. Here by the bar here, P bar, let P bar represent the bitwise complement of P. So for instance, if P is 64 bit of zeros, and you complement it, you get 64 bit of ones. Okay, by bit complementation, you replace 0 with 1 and 1 with 0. That's the whole idea. And this has the following property. If you encrypt the plaintext block P with a secret key K and obtain the ciphertext C, once you take the complement of this P and the secret key, then the resulting ciphertext is the complement of this C. So this shouldn't happen actually, okay? So some people, they say that this is not a bug, it is a feature. So they say that once you implement this, you can check if you implement it correctly by checking this property. But of course, this actually, how the cost of exhaustive key search. So if you have, capture all of these plaintext and ciphertext, instead of performing 2 to the 56 encryptions, you can do 2 to the 55 encryptions and check if capture the secret key. But of course, again, you can think that it is a feature and implementer can use this property to check if the implementation is correct. People discover some weak keys, and these are really weak keys. So a key K is called a weak key if encrypting twice with it leaves the plaintext unchanged. So but of course, this definition is not general. This is for this. In general, we call a key is weak if it's acts differently than all of the other keys, okay? So in terms of statistics, okay? But in these weak keys work in a really bad way. So assume that you have the plaintext P. So you choose one of these weak keys. You encrypt this plaintext with, for instance, this key. You obtain a ciphertext. Then if you encrypt that ciphertext with this key again, you return back to the plaintext. So this shows that the design has too many symmetries inside it. And this is not something we would like to have. And moreover, each weak key has 2 to the 32 fixed points, showing that if you do only one encryption, 2 to the 32 out of 2 to the 64 possible input blocks, these 2 to the 32 of them goes to itself. So you have a fixed point. So you try to encrypt something, but you end up with the same thing. So you don't have encryption for these fixed points. So these are really weak keys, okay? Again, let me give you a test vector as I did for the present. So I think most probably I took this from NIST documentation from years ago. Since it is no longer a standard, those documents are outdated, but I think you can still download them. So one way of checking the correctness of an implementation is to use the test vectors. For the plaintext P, this is the plaintext block. If you choose the key as this, starting from 0 to F, you have the round keys as follows, and you have the round output as follows. So when you want to implement this, you will check if your implementation is correct by checking these test vectors, okay? So the last output is your ciphertext. So this was deployed in many applications, and it wasn't easy to change it with another cipher. So in software, we can modify this, right? So in software, if you're using this, and if you have AES, you can say that, okay, let's make an update to our software and use a more secure cipher. So in software, it is not that hard. But of course, it depends in this situation. For instance, in Windows, if you are using MD5 in an earlier version, and once MD5 is broken, I'm talking about hash functions here, not block ciphers. Generally, you have to, come up with the new Windows and change the hash function there, because it will be very hard to change the cryptographic algorithm in a very huge software like an operating system like Windows, XP or 3.1 and so on. But in a simple software, changing the encryption algorithm is not that hard. But if you have it in the hardware, if it is written into the silicon, you cannot change it. This is why once you realize that an algorithm is going to be broken, you start to, install new devices so that in the following years, all of the old devices will be removed, and so that you can communicate in a secure way. So in order to overcome the exhaustive search for the 56-bit key DES, multiple DES encryption with different keys are suggested. But the expected security level is not possible in practice. For instance, double encryption with 2 keys does not provide 112-bit security. So people thought that instead of using this, let's use this twice and choose 2 different 56-bit keys. So in total, we have 112-bit secret key, so that now we doubled the security. I mean, in terms of course, talking about powers of 2. But it turns out that this actually provides you 57-bit security, okay? Currently, the most used DES variant, which is also standardized by NIST and ISO, is the triple DES algorithm. And it works like this. Use DES 3 times consecutively using 3 keys, key 1, key 2, and key 3. So using DES, a plain text is encrypted with K1, but then decrypted with K2, and then encrypted with K3. Of course, I use the decryption here deliberately. You can use encryption again, but in this, encryption and decryption actually are not that different. So if we go back to main picture of the phased ciphers, here we have the DES. Let's talk about this. Going from here to here and from here to here is actually identical for the hardware. Only change is that if you're going from here to here, the round keys you are using are K1, K2, K3, and so on, so in this order. But if you are going from here to here, you perform the same operation, but instead of K1, you use K17. So you are only changing the order of the round keys in the phased ciphers. So this way, in terms of security, in the triple DES, I can write encryption here, but I deliberately write it, which I will show in the following slide. So if you write it as encryption, decryption, encryption, again, as you can see, plain text is encrypted with 1 key, then decrypted with another key, then encrypted with another key. Sorry, encryption, decryption, encryption. I think I wrote the orders wrong here, so it should be K1, K2, and K3, but it doesn't matter. It depends on how you use it. So NIST said that it will be standard until 2030 because they say that they support 112-bit security until 2030. But when 2030 comes, they will think about if they will accept 112-bit security still. So it might. Currently, we have a lightweight cryptography standardization process. So they are expecting 112-bit security. So in 2030, if there isn't much technological advancement, they may say that, okay, we will support this many key length in the future years. But in a different document, they say that triple DES will be removed after 2024. Okay. So this encryption, decryption, encryption actually provides backward compatibility because if you choose all of your 3 keys identical, let's look at the picture. What we are doing is encrypting with K, then decrypting with the same K. So you end up with P again. Then you encrypt it with a single key, which turns triple DES into DES. This is important because this is still used in many banking applications in the background, in their own server, not in the internet connected world. But because they implemented it years ago and they, don't want to touch it because they may break the financial world if they try to update it. So this is why, if it is working, don't touch it. Ideology works here. So this is why this works in the background. But to be compatible with it, you can implement triple DES, but choosing all 3 keys identical turns triple DES into DES. So in terms of security, encryption, decryption, encryption is no different than encryption, 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 but we lose the backward compatibility in this scenario. This is why when you talk about triple DES, it directly means that encryption, decryption, and encryption. Okay. So here's a picture of how much security these variants actually provide. So assume that you are only using 2 encryptions. So in theory, you can perform a brute force attack with 2 to the 112 tries because these are the length of the secret keys. But what you can do is that you can perform a single DES encryption with every possible key, 2 to the 56, and record everything into the memory, the output. So once you need to attack the 2 DES encryption, since you already performed the first part and recorded everything in the memory. You perform the exhaustive search in the second part. This is why the time complexity is reduced to 2 to the 56. But of course, if you add this part to this part, in theory, you are performing 2 to the 57 encryptions. But of course, you can say that this is a pre-computation. I do it once and wait for this cipher text to leak, for instance, then perform the exhaustive search at that time. Of course, in this scenario, you need two known plaintext. In this case, you need to have two chosen plaintexts and so on. You can perform 3-DES operation, but use 2 different keys. The security is still here. So if you use triple DES with 3 keys, again, now you have 168-bit secret key material. A direct brute force attack would require this many operations. But you can do the trick I mentioned here. So you can, consider triple DES as a single DES and then 2 DES. So perform the pre-computation on the single DES part, record everything, and perform an exhaustive search on the remaining part. This is why I say that triple DES has 112-bit security, okay? This is the whole idea here. So, but 112 bits, okay, today it is secure, and triple DES is used in many applications since it is a standard by NIST and ISO. So in Turkey, in credit cards, I checked this contactless payments, these NFC payments, and some credit cards in Turkey use AES, and some of them use triple DES. Okay, so it is really used in practice. You might say that why they don't use AES? Probably producing a smart card or a contactless payment card with triple DES costs less compared to AES, because here the DES is really small and you're using it 3 times, so maybe the production cost is lower compared to the AES version. But if NIST removes triple DES in 2024, most probably, credit cards in the future will, all of them will move on to AES instead of triple DES. Because once NIST changes the standards, the rest of the world follows them. So most probably in the ISO standards, it will remain for some time, but probably in 5 or 10 years, ISO will also remove triple DES. So if you don't need a special reason to use triple DES, just don't use it. Just use AES. That is the whole lesson here.